everyone. Welcome everyone to the first webinar on the Transforming System Through Partnership Newton Fund Royal Academy of Engineering program. And today we will have a discussion about the novel titanium alloys and then net shape manufacturing technique for biomedical application. And my name is Chinapat Panviswas, Senior Lecturer in Material and Solid Mechanics at Queen Mary University of London. As the UK partner of two TSP project here, I would like to introduce the first speaker. She is from Royal Academy of Engineering to give us an open remark. Ms. Cordelia Bush, Senior Manager at Engineering X program at Royal Academy of Engineering. And the floor is yours, Coco. Thank you very much.
Thank you so much, Chinapat. I'm just going to share my screen. So thank you very much for the introduction. As Chinapat said, I'm Coco. I'm a Senior Manager at the Royal Academy of Engineering, working on Engineering X. And let me see if I can change this. Yeah. So Engineering X is an international collaboration founded by the UK's Royal Academy of Engineering. So we're the UK's National Academy for Engineering and the Lloyd's Register Foundation. So we work to support engineers who are addressing global challenges with a big focus on safety and sustainability. We aim to collect evidence on the issues that we're working on and to build diverse and multidisciplinary communities around each challenge. Transforming systems through partnerships is one of 5 missions under Engineering X. The others are pandemic preparedness, which focuses on the pandemic, safer end of engineered life, which looks at what happens to engineering products and infrastructures after they've reached their useful life. Safer complex systems, which looks to understand successes and failures within complex systems, and engineering skills, which aims to embed safety skills and education in engineers at university and in their professional careers. So before I talk to you about TSP, I'll tell you briefly about the funders for this programme. So we're funded by the Newton Fund, which is administered by the UK government's Business, Energy and Industrial Strategy Department. The Newton Fund aims to support equitable partnerships in middle-income countries in Africa, Asia and Latin America, supporting research on agreed national strategies and priorities, and encouraging skills and capacity development and technology and knowledge transfer between the UK and partner countries. Each UK delivery partner in the Newton Fund works in partnership with an in-country partner, and the in-country partner provides match funding and other support. For example, in the case of TSP, our in-country partners help us reach much further with our application process, as we don't have any countries in other offices, and also helps us to support the entrepreneur, the researchers, and to follow up with their projects as they're going through them. Thailand is one of 16 Newton Fund countries. And by the way, we have, as the Academy, we have no decision over which countries form part of the Newton Fund. So I've taken this information from their website, but it sounds sensible, and I'm sure it's all correct. So Thailand was chosen for its strong potential for outstanding science and innovation capacity, based on their analysis, and also for its huge economic success, strong growth and poverty reduction in the last decades. Other countries in the Newton Fund within Asia include the Philippines, Malaysia and Indonesia, and then there's also South Africa, Kenya, Jordan, Peru, I believe, and various others. So in each country where the Newton Fund works, there are agreed priorities for the fund. So these are considering that country's particular national strategies and goals. So for example, in Thailand, these include climate, environment and weather, science, tech, research and innovation, health security, and sustainable agriculture. And you'll see later that these priorities also overlap quite a lot with the focus areas for transforming systems through partnerships. So what is TSP? TSP builds partnerships between academia and industry to promote challenge-led innovation, facilitate collaboration and knowledge exchange, and increase industry input into teaching and curricula. So we aim to support researchers and innovators that are working towards the Sustainable Development Goals, whether that's to do with health, energy, water, climate change, agriculture, etc. The industry partners working on TSP projects range from startups and university spin-outs, like Meticulous in this case, to large national or multinational companies. Where possible, we also encourage projects to collaborate with NGOs or local government. We believe that problems can't be solved by people working in isolation, but by bringing researchers and industry partners together, we can support them to solve challenges more quickly by considering new and different angles, incorporating different expertise. We also aim to support and upskill the next generation of engineers to solve global challenges. So a lot of TSP projects include webinars for students or creating new modules or curricula based around the particular challenge and the inputs from the industry partner that they're working with. And in Thailand, our partner for the program is the National Science and Technology Development Agency. The Newton Fund, the Transforming Systems Through Partnership program, has been in existence since 2019, but it is an iteration of a previous program called the Industry Academia Partnership Program, which had similar goals. So as you can see, we've funded a lot of different projects. You can see in Thailand alone, we've supported 39 projects. That's 1.7 million pounds worth of grant funding to Thai researchers and innovators, with a total investment of 5 million. So that includes match funding from the National Science, Technology and Development Agency, as well as each project often brings in match funding from the industry partner as well. And due to the pandemic, a lot of these grants are still ongoing. So I think we probably have about 90 grants ongoing. This is just a little overview of some of the key challenge areas that we have in the Transforming Systems Through Partnership portfolio. So as I mentioned, nearly all projects have some kind of an education angle, but then there's also a big focus on health and well-being, on energy, decarbonisation, net zero, on agriculture, food and land, on increased sustainability of cities and communities, and on digital revolution, emerging tech for sustainable development. And finally, I'll touch briefly on the two projects that you're going to hear more about today. I'm not an engineer, so I won't go into any details on what they really involve, because I'm sure you'll hear much more later. But I was just going to talk about the strengths of the projects and why they were chosen. So the first is the novel low modulus titanium alloy for biomedical applications. And this was seen as a really strong UK-Thai collaboration, encouraging the advancement of materials and manufacturing technologies. It was a really strong involvement of a very significant Thai industrial partner. The reviewers saw some really novel engineering in terms of the improved materials and the geometries, which are much more compatible with bone growth for implants. They also saw huge potential for a significant increase to engineering expertise in Thailand, and also for improvement in health outcomes for the elderly population. And within Thailand's national strategy, thinking about health security, one of the key focuses is how to prepare for an increasingly aging population. So that was a really key factor. And the second program, digital materials design and additive manufacturing for helping patients with bespoke 3D printed implants. The researchers were the reviewers were particularly impressed by all of the partners. They're all very well established and each bringing excellent complementary and relevant research capability. Again, involvement of a strong industrial partner, and they could see strong health and economic benefit, as well as increased engineering expertise in Thailand through developing and commercializing a customizable implant and the knowledge of how to manufacture this, and also integrating that within the national healthcare system. And finally, also, of course, significant potential improvement in health outcomes for the elderly population. So I will stop there, and I'm not sure if there's time for any questions, but I'll stop sharing and pass back to Chinapat.
Thank you very much, Coco. It's very comprehensive summary of the project overall, and also you give some detail about our two projects that we are going to discuss today. We can have probably a short one question. If anyone has any question, you can type in the chat box, or you can raise your hand using the button in front of you, and then we allow you to speak. If not, I mean, we may take some question along the way if anyone has it. But I mean, thank you very much, Coco. And let me introduce our key partner, UK partner, which is actually support us for a long time, and he also a fellow of Royal Academy of Engineering. Let me introduce Professor Roger Reed, Professor of Materials and Engineering Science at University of Oxford. Roger will give a talk on the alloy by design, a low modulus titanium alloy for additively manufactured biomedical implants. The floor is yours, Roger. Thank you very much.
Okay, and hopefully you can see my my slides.
Yes, we can. Yes,
okay,
that's correct. Thank you very much.
So thank you for that kind introduction, and I want to introduce some of the people from our end working on this project. Chinapat has kindly introduced me, Roger Reed. I am one of the professors at the University of Oxford. I should also introduce Enrique Alibor, who used to work in my research group at Oxford, but is now working for our spin-out company, which is known as Alloyd Limited. And they are doing historically some of the alloy design work that I will present today in collaboration with our partners in Thailand. Tony Kang is a postdoc in my group at Oxford, and Daniel Barber also used to be a postdoc in my group, but has recently been appointed to a professorship at one of the most famous universities in Spain, the Polytechnic University of Madrid. So he's doing very well there. So I'd like to say also that, of course, there are many collaborative links with our partners in Thailand who also have been involved in this work in a major way. So there are 5 points for my talk today. I'm going to talk a bit about the background to why we need to think about titanium alloys for biomedical applications, and why I think additive manufacturing is so important given the era of personalized medicine. I'll give some of the details around how we have gone about designing new alloy systems for these applications. Of course, it's very important to go further than just theoretical work. We have to show how we have tested the alloy for its strength and biocompatibility and so forth. So I will do some of this, and then I will draw some conclusions. So I hope that is going to be fine for everybody this morning. Well, of course, one of the major points here is that when we think about doing sawbones type experiments in the lab, we have an implant here. We use a synthetic bone and test this material. You can see there is a big mismatch in properties because, of course, the metal is very strong. It's very stiff, but the bone, of course, is not of the same caliber. It's much less stiff, and it's more brittle. So it has a tendency to fracture in a brittle fashion. We have to think of such phenomena as stress shielding then. The implants can loosen over time. There can be issues around toxicity, and the bone can tend to resorb. So there has been a temptation in this field to take titanium alloys, most of which have been designed for aerospace applications, and simply implant them into the body. And the difficulty is, of course, that some of the elements that we use to strengthen titanium are known to be cytotoxic. So one approach should be to try to identify new compositions which are more suitable for these sorts of applications, with also elastic properties which are closer to that of bone. And in Oxford, we have made some strides with regard to this by considering the goal of using additive manufacturing to 3D print titanium structures which are hollow and which have a combination of yield strength and elastic modulus, which are more consistent with that of the bone materials, which are for the cancellous bone around perhaps 1 gigapascal, maybe a bit less for cancellous bone, and up to perhaps about 20, 30 for the cortical bone. You can see from our experiments here, which we published in Scripting Material, we were able to design a range of hollow titanium structures which bridge the gap between the properties of cancellous bone and also those of cortical bones by making these what we call metallic bone structures. So this has given us a lot of confidence that it's possible to use additive manufacturing to tailor properties for these applications. Of course, we have to make use of additive manufacturing. We have to think about which of the existing alloys are suitable for these applications, maybe tailor them by taking some scientific input from them, or maybe think about the non-suitable conventional alloys and modify their compositions to get the optimized alloys for additive. So we've been going down this path, also thinking about the kinds of properties of the alloy that would lead them to be amenable to this new process. So what are the factors which are important? Well, of course, this is a new field and no one knows for sure. But when we sat down to think about this, the certification theory people tell us, of course, that the certification range is important. So that means over what temperature range are we likely to be solidifying the material. Usually we think about a narrower range of certification temperatures being better suitable for processability. We can also think about the way in which the fraction solid varies with temperature during solidification. We know that as we approach a solid fraction of 1, the material becomes more susceptible to the likes of hot cracking. So we can design hot cracking susceptibility indices which tell us something about the risk of solidification or hot tearing type phenomena. And also we can think about tailoring microstructure. So we can think about growth restriction factors which tell us something about the transition from columnar growth with a relatively planar solidification front towards one where we have more equiaxed microstructures, which we believe to be more suitable for crack-free microstructures. So this is some of the parameters that we consider in our alloy design approach. There are many others. We think about, for example, designing the alloy for low elastic modulus, because that's, of course, helpful for compatibility with the bone. We don't have really good theoretical models for the biocompatibility, but there are empirical trials that have been done to look at the growth of cells on metals, and from these sorts of experiments we know which sorts of elements we should be adding to the alloy. We should be considering cost, also the strength, and then the factors I referred to in the previous slide. So you can see from this slide that the problem is multifaceted, it's interdisciplinary. There's probably no one right answer for this problem, because we have to think about applying weighting factors to each of the important factors here. So the strength by grain refinement, the cracking susceptibility, powder production, the biocompatibility, and the strength recovered by heat treating. And of course, it could well be that different situations demand different emphases on each of these things. But of course, the important point is we shouldn't just guess. We have to put in place a science-driven approach for alloy optimization. So in what we do here in Oxford and in Alloyed, we have a number of baseline alloys. We design an alloy space, and we make calculations for each of the relevant merit indices and try to come up with estimations for where we should be. So here's one example of what we do. The grey space here gives you the range of properties which are calculated using our software. And then we plot here the growth restriction factor estimates as a function of the predicted strength of the material. We have minimum values that we deem to be acceptable in this application. And you can see here the blue space are the alloys that we considered for these applications, and the black dot is the one that I will talk about the properties in this particular talk. And I'm going to emphasize again that this is a tough problem, because you have to trade off many different properties here. You can see here, for example, that as we go towards the beta system, the stiffness drops as we would like, and that's arising from an increase in the d orbital energy level and an increase in the bond order, the average bond order in the alloy. If you want to read more about this, you can look at our recent paper in Active Material, which has been published this year. Well, of course, we should check the properties of our alloys. We have been working with the company HC Stark in Germany. These alloys are pretty tough to manufacture and very expensive to manufacture, so you have to go to experts to get these things fabricated. We chose to work with HC Stark, who've done a good job to produce the powder of a size, a mean size about maybe 30 microns, and we found that to be suitable for our additive manufacturing that's been done with the Renishaw system here in the UK. So here are typical compositions. You can see we've added niobium, tantalum, palladium, zirconium, and some tin. There is some chemical heterogeneity arising from the analysis you can see of the powder, but in general not so bad, and we have good experience actually of proving the additive manufacturing of this new alloy, and also the flowability appears to have worked well. So we have gone on to develop a process for the additive manufacturing involving single track builds, the building of queues where we can start to get properties, and then further some larger build volumes that we can test the mechanical properties of this new alloy. So this is the first part of our processing trials. We do a lot of trials at different laser powers with just a single track, and then we analyze the size of the single tracks. You can see this here. We identify using high throughput microscopy the conditions which lead to either a stable melt pool, which is of course what we want. We can see whether the pool is unstable or very unstable. We eliminate obviously those possibilities. And then when we proceeded to the building of simple cubes to further assess manufacturability, here we used the commonly known titanium 6-4 alloy as a reference. We do the printing as a function of speed and power. You can see that titanium 6-4 is prone to porosity, consistent with the literature. We can find regions where it prints reasonably well, but there is a lot of the parameter space where we see considerable porosity. That's also true of the new biomedical alloy, but much less so. You can see there's the alloy is more processable in the sense that there are fewer conditions which are prone to porosity, and we can build up processing maps to identify the regimes where we should be printing this alloy. We have also made a lot of assessments of the mechanical properties of this alloy. For this, we use a miniaturized electrothermal-mechanical testing system in my group in the University of Oxford. This makes use of dual heating by the resistance effect. Typically, we would test strips of material, perhaps 2 millimeters by 1 millimeter. We make use of pyrometry and digital image correlation to measure the localized strain. And from this, we're able to deduce the stress strain behavior of the material. So you can see here lots of stress strain behavior. You can see the flow stress is between 800 and 900 megapascals, quite a range of ductility. No particular correlation with the laser power for that, and some low values of stress at the highest power that we use, which I'll discuss in just a few moments. We've also done trials to check out the anisotropy of the properties. So we print the material either vertically or horizontally, and we then check the properties after subsequent machining into our specimens. You can see here that in general the ductility is improved for the horizontal direction, and rather a bit more inferior in the vertical direction, and I think that's quite commonly found for these sorts of applications. Typical microstructures, we do a lot of microstructural analysis. In the interest of time, I won't go into all the details here, but you can see, for example, that we tend to end up with a coarser microstructure at the higher power, and also after heat treatment. Typical fracture surfaces here. In some instances, we are able to see cavity nucleation and grain boundary failures. In some of the conditions we have noted and been able to avoid in other second generation alloys the presence of oxygen-rich alpha phase at the grain boundaries, which is some cause for concern in these sorts of systems. And again, we discuss this in more detail in our recent paper. So this slide is nearly my last one. It summarizes, of course, the advantages of the new alloy systems that we are all working on. You can see that the low modulus alloys do indeed have a lower slope. That's consistent with what we've designed for. the trade-off seems to be a slightly reduced flow stress. We seem to be able to get to greater ductility, which we believe will be good for fatigue type resistance. And of course, the eventual applications for these alloys involve the likes of spinal implants, which we need to design for, and future work could also involve incorporating the stress transfer between the metal and the bone. That's something we want to get a bit more into. So just a few brief conclusions. I won't read all of these out, but we have been using our alloys by design approach to design a metastable beta-phase alloy for these applications. We take account of a number of factors for this, including the passivation of the material, the elastic modulus, the Martensite reaction, and so forth. We've done lots of trials to check out the compositions of the or processing of the new alloy and the properties. We've developed relationships for the laser parameters and the properties. We think that's important for the potential applications of these materials in the body, and we have gone about optimizing the microstructure for these applications, which involves balancing the key ingredients of the elastic modulus, the strength and ductility, and engineering in also the degree of anisotropy that we have to manage. Okay, so that's it today, and I'll very happily take some questions.
Thank you very much, Roger. This is very nice presentation. Are there any questions for Roger? I mean, we have about 7 minutes for question to Roger. If you want to ask the question yourself, please use the raise hand button, and then we allow you to speak. Yeah. If not, I mean, I have a question for you, Roger. In your presentation, you talk about, I mean, a computational approach for the low modulus titanium alloy. Have you actually applied or used these materials in a body yet, or are there any plan or project that you have been doing? I understood that you have worked with some medical doctor as well. Yeah, thank you very much.
Okay, yes, I can give you the latest situation with regard to this. The company Alloyd has in the last 2 years implanted I think something like 20-25 implants into the body, but not with this new alloy yet. They have passed all of the due diligence and checks needed to design and print the implants for insertion into the body, working with a number of different surgeons around the country, but only so far with the titanium 6-4 material. That decision was made because you know, one needs to start somewhere, and the titanium 6-4 material is already passed for use in the body, even though we know that it's not totally the ideal situation. So we chose to start there, but of course we have a plan to insert these new alloys into the body when the time is right. What I would say is that we have conducted a number of trials in the usual way to check for the biocompatibility, and all of those checks have been passed. We just haven't yet taken the step to using the alloy for these applications.
Okay, thank you very much. Are there any question for Roger with regards to this? I think that I have message from Dinah. She said, "Thank you very much for your very interesting presentation."
Okay.
In terms of the when you take this, I mean, I know the difficulty when you want to introduce the new material to the body, for sure. I mean, I think I understand that in your lab you also have the I would say biomechanical testing as well, and then that is the simulation you show at the very beginning of your presentation. Have you, I mean, used the new material to test this one yet or not? So what is the situation for this?
I think Chinapat is referring to the trials that we have done in my lab. These
Yes.
were, I would say, these trials were. I can get some information about these trials. Again, there is some publications of this. In
of
the
course,
UK, there are 3 or perhaps 4 manufacturers who are passed the checks to design and sell hip implants. But of course, the hip implant is always of a different geometry or size on the manufacturer. So we have been asked by some of the medical hospitals to consider the mechanical integrity of the metal bone arrangement for thinking about the optimization of the shape of the metal implant, because the risk of post periprosthetic fracture is large now, because of course there are many people who have had their hip implanted in this way. They're subject, they can be subject to further falls, of course, and there's a risk that, of course, the remaining bone will fracture. So whereas in the past, perhaps 30, 40, 50 years ago, when these implants were first done, people didn't survive long enough to have to worry about subsequent fracture. These days, the patients are surviving into very old age, such that when they fall on their femurs, there is a risk of fracture, which should ideally now be taken into account. So that was the reason why we have been doing that kind of work. We haven't, of course, used new alloys for these applications because, of course, companies like Stryker and Zimmer, are very well established in this field and have their own methods of manufacture.
Yeah, sorry.
I think this is the cause of.
Sorry, Chin.
Yeah, this is a cause of collaboration as well that we are going to do in this project. Yeah, sure. Please, Dr. Anjali.
Okay, yep. Roger, there is a question from Dinah about the fatigue properties of the new alloy. So Dinah, we allow you to ask the question yourself, so you can open your mic. Dinah, you there?
I'm a PhD student, University of Birmingham, and I'm currently working on titanium 64 as well. And I was just wondering about the new alloys, which are low modulus titanium alloys, and their fatigue properties. And is there any interest to look into this aspect, especially for hip implants and medical applications which require fatigue, high fatigue properties?
I think the answer, Dinah, is yes. That work should be done. We haven't published any fatigue data yet for the new alloys, but I think there is a big testing program going on in alloy to look into those fatigue properties. So I think in the universities, it's really important that that kind of work is done, because probably the fatigue properties are one of the most important aspects to be considered when making these decisions.
Yes, thank you so much. Can I also ask another question?
Sure.
About the single tracks. You talked about the columnar to equiax transition, which is very important for isotropy or homogeneous properties across the implant. So I just wanted to know if so the findings here suggest that the transition could actually occur due to varying process parameters such as power and scan speed, and is that correct?
Yes, I think that's correct, but you know, I think more work needs to be done to really confirm that in my opinion. But yes, I think what you say must be correct.
Yeah, right. Thank you so much. Thank you so much for a very interesting presentation. Thank you again.
Thank you very much, Dinah and Roger. I mean, that is very, very insightful presentation. I would like to, we may, according to schedule, we may move to the next speaker from the National Metal and Material Technology Center from Thailand. May I introduce Dr. Anjali Manonukul, a leader of Smart Alloy and Manufacturing Research Team at National Metal and Material Technology Center, or MTech. Today, she will give a talk on the metal injection molding and metal material extrusion additive manufacturing of titanium alloy. Thank you very much, Dr. Anjali. The floor is yours.
And good afternoon, people in Thailand. Okay, we've been working with Oxford, with Roger and with Alloy on things even before the Newton project. So Alloy designed the powder, the alloy and produce the powder. So what Roger have been talking is they've been focusing on SLM technique. In our lab, we are metal injection molding lab. So we're focusing on things that need debinding and sintering. Okay, so that is what I'm going to talk about today. So there are two sections. One section will be on metal injection molding of titanium alloy, and we will touch on the fatigue properties as well. And the other section will be on additive manufacturing, which is focusing on the material extrusion. So it needs debinding and sintering as well. So for metal injection molding, if just would like to give you the introduction if you don't familiarize with the process. It's about 40 years old. The technology itself is being commercialized in industrial at the moment, but a lot of people still don't know the process. So imagine that most people know plastic injection molding. So imagine that you have that mold and now you can produce plastic, you can produce ceramics, and you can also produce metals using the same mold. Okay, so in order for the powders to be able to flow in injection molding machine, we have to put the polymer in as well. So the step is including metal powder mixing with the binders, and then we have the feedstock, and then we inject in the injection molding, and then we remove the binder either by solvent debinding or thermal debinding, and then we have the skeleton of the powder, so we sinter the product to be the product. So this is just quick picture, you see. So you can have the recipe of binders, several kind of polymers together mixing with the powder. If you put ceramic in, then it become white, and then granulate it in feedstock. And injection molding, so exactly the same injection molding, plastic injection molding, but we have to allow for the shrinkage of the binder because we have to remove all the binder. And thermal debinding and sintering. So it's white because it's ceramic. So just would like to remind you that it could be either ceramic or metals as well. Okay, so the left-hand side is actually what we call the green part before sintering, and the right-hand side and the left-hand side is the metallic silver part is the sinter part. So it shrink a lot. It shrink about 13%. So the technology in metal injection molding is mainly the binder and how we control the size shrinkage. And the sintering itself as well. Okay, so example of the application. So this is some of the medical application using titanium 64. So titanium 64 is being mimed medically for medical application at the moment. So they've been using in many applications. Okay, for example, this one is a tool from Stryker. Stryker have many pieces that made of titanium 64 in this instrument. And we also, another application we've been focusing on is wearable. So this variable, like the watches and like the hinge of the glasses, they have been producing by metal injection molding and titanium 6-4. So just so the powder itself, materials that can be MIM are those that's sinterable. So we are not talking about MIM of aluminum or magnesium. Okay, so those things is difficult to sinter. So anything that relatively easy to sinter should be able to do MIM and MIM. So the metal group is like the biggest one is stainless steel, and we also have many section of the market that doing titanium and titanium alloy, so it's titanium 6-4. Okay, and we have ceramic material like alumina and zirconia as well. So our lab start in 2003. We got the NATO project from Japanese government. So we got €1 million funding from the Japanese government that literally transferring the metal injection molding technology from Japan to Thailand. And we have every equipment being transferred from Japan to Thailand. And we have industrial partners and university partner from Japan. So we have Osaka Yakin at Mix. So these companies are either they are member of the Metal Injection Molding, Japanese Metal Injection Molding Association. And we have university like Kinki University, Kansai University, and University of Tokyo. In Thailand, we have Chulalongkorn University as our partner at the beginning. So the objective is to set metal injection molding technology in Thailand and to support the MIM industry in Thailand. So overnight, we have the whole lab set up. So everything shipped from Japan. So we have the basic equipment mixing, the injection molding, debinding, and sintering furnace. And we also have some seminar, and then our staff being sent to Japan for the basic training. So what we have done after that is we work with a company called Custom Thailand, which is a MIM company. At that time in 2004, this company cannot do titanium MIM yet. So we have a co-research project with the company to do commercially pure titanium and titanium 6-4 metal injection molding. The difficulty is how we sinter titanium and titanium 6-4 and how we reduce the contamination from the binder to the metals so that it's not brittle. So after we did the work for Castem, so the company is called Castem. So we did the lab scale in our lab, the finding of the mixing, injection molding, and debinding and sintering condition, and we test the tensile properties, and this is what we got in our lab. After so trial, then we can have elongation to up to 18%. So this is really good at that time. We actually did it much better than all the Japanese company. So we have transferred the technology to Castem. So they do mass production in Castem, Thailand. Now and this is what happened when the first few times that we did it in Castem, Thailand, then the elongation dropped down to about 4% because of the contamination. So we have to identify where the contamination in, because the company been producing ion-based MIM, so it's contaminated from ion. So after solving all the contamination problem, then what we get is the one produced in Custom Thailand is within the range that we can do in our lab. Okay, so Custom Thailand at that time in 2004 become the second company in Asia that can do titanium MIM, and now they still mass producing titanium MIM, titanium 6-4 MIM for it as commercial products. The other project that we do is this one is with Oxford University and with Alloy. So the powder itself that Roger been talking about, the new computational design powders actually been produced in Germany, and then the powder have been SLM in Oxford, and then some of the powder have been sent to Thailand for metal injection molding. So this work we've been trying to compare how the two production process can produce different properties. So I will skip the introduction because Roger already talked about this, okay, the alloy design part. So the conclusion of that part is we published the paper together. So mainly for the MIM, we have several issues with the MIM because the MIM, they are so sensitive to, the beta titanium is so sensitive to binder and very slow cooling. So mainly when we have slow cooling in our sintering furnace, then we have low elongation because we have the formation of titanium carbide. Okay, so at the moment, at the current project, the Newton project is we trying to somehow control this formation of titanium carbide and trying to increase the elongation. So we will become comparable to SLM. Okay, there are reasons that why we want to fabricate the part by MIM. MIM should be really a lot cheaper than SLM. SLM is suitable for personalized implant, but MIM could be for things that we don't need to personalize, but it will going to be at low cost. So that is why we interested in developing this part with Oxford and Alloy. Okay, and the other thing that we do with is also we focusing on we working with another company called Taisei Kogyo in Thailand, a MIM company. We study Taisei Kogyo want us to increase the fatigue properties of titanium 64 MIM. Because of all the powder technology, when we do the formation, when we do fabrication, most of them will have some porosity, or so the fatigue property is normally lower than warm metal of titanium 64. So there are ways and means in MIM that will increase the fatigue properties. For example, we do some grain refinement. So they are like adding the boron, or we do what we call the modified sinter condition. So normally titanium 64 we sinter at about 1150 degrees Celsius for 2 hours. But if that is in alpha phase region. But if we sinter them at lower temperature, about like 900 degrees Celsius, for longer time, like 12 or 24 hours, we can control the grain size to be much smaller. Another ways of increasing the fatigue properties is using surface modification. So if we use fine shot pinning can actually increase the, sorry, my mouse not move properly when it go to this one. So the fine shot pinning can increase the fatigue property as well. Okay, and some alloying. So this is what we do with Taisei Kogyo. They have customer that want to use titanium 64, but because of the application, it needs really high fatigue resistance. So what we do is we do several modification, several grain refinement and like all the technique that try to increase the fatigue properties. So we have commercially pure titanium and titanium 64 as the baseline, and we also adding some molybdenum in to modify to make it beta titanium, to make it different percentage of alpha and beta, trying to increase the fatigue properties. So this is the tensile properties. Okay, so what we found is by adding molybdenum into the titanium 64 and the titanium 64 without molybdenum, but we do the sintering at modified condition, then it will have outstanding tensile properties. Okay, so and when we do, and then when we have good tensile property, we move to the fatigue properties. So first thing is, if you look at the microstructure, you see that the microstructure is totally different. This is typical microstructure for 64 MIM. Titanium 64 MIM is slow cooling, so it's really different from what Roger have shown for SLM. SLM is very fast cooling, so structure is different. And when we do like modified sintering, we have very small, very fine grain. And when we add molybdenum, then we have different microstructure as well. The bright spot is the molybdenum rich area. Okay, and so from the graph, you can see that if we compare with the basic conventional titanium 64 MIM, the gray one, you see that the one that gives the best fatigue properties is the molybdenum containing titanium 664 with the optimum sintering condition, and also the molybdenum free titanium 64 that been sintered with low temperature very long time, that give us the good mechanical properties. Now for manufacturing company like TSP, they keep saying that they hate our modified sintering condition because they doesn't want to occupy that furnace for 24 hours to sinter titanium 64. Okay. So another thing that we do in our lab is that we start doing it for the past 3 years is material extrusion additive manufacturing. This is because we've been doing MIM, so we know about debinding and sintering, and this is the closest one to our technology. If we jump to SLM, then they're totally different mechanism. So in metal extrusion, AM, the process of feedstock preparation is very similar. We mix powder with the binder, okay? But for MIM, it's only granulated. But for 3D printing, we can do filament, and then it's all a cylinder bar, okay? And then we can print it. When we print it, then we go to the same process as MIM, is debinding and sintering, okay? And this is how just to compare the product, similar product. So the turbocharger, if it produced by MIM, the surface finish is very good because we use metal mold, but metal mold is expensive. But if we do 3D printing, we don't need metal mold, but because it's 3D printing, it have layer by layer feature that come with the technology. So it's still in developing stage in most academic. Okay, there are 2 companies that commercialize selling the machine commercially for metals. The company is called Desktop Metal and Markforged, but they are closed system. Okay, so most of the academic people, they want to develop their own filament, but there are problem associated with it. Is when you produce your own filament, then you have inconsistency in mechanical properties. And when we compare the base MIM for titanium, the base metal extrusion for titanium at the moment, the elongation is better than MIM, but the strength is better than MIM as well, but it's still not as good as wall metal. Okay, so that is from literature. So we are trying to get to that as well. Application is like this example of the application for material extrusion. The one that are commercialized already is 316L, but titanium is still developing for medical application as well. So there are still a way to go. It's not as advanced as SLM titanium 64. Okay, some application for 316L for the more medical application. You will see similar application from Professor Bunrat in the next speaker as well. He's also do personalized implant as well, but for SLM process. So overall, is what we want to do in MTech is we want to develop the metal extrusion. So we have several partners. We have like the filament part. We have partner from Japan. So we have professor that specialize on compounding polymer. Okay, from Yamagata University that help and researcher in MTech that specialize on polymer that help us with developing the filament. We're working on the commercial system as well, the Desktop Metal and the Markforged one. We also to learn about the processing itself and the sintering. And we also have in our group, we have the surface modification part. So we have like mechanical surface modification using fine shot pinning for better fatigue properties. And we have the chemical surface treatment for anodizing and for electroplating. We also do simulation with Professor Chinapat and with our colleague in Thammasat University for the process like the printing, the debinding, and the sintering. And we have our colleague that working on like building some of the machine and the automation, developing the automation part as well. So that is still at the beginning. So we are trying to move forward this way. So I would like to thank everyone sponsoring the project since 2003 and until now, and all the collaborators and our past and present members. Thank you.
Thank you very much, Dr. Anchi. This is very inspiring presentation. I would like to take some question from the floor. If you have any question, please raise your hand or type it in. I will read it out for Dr. Anchi to answer it. Yes, please. Yeah, if not, may I ask a question? So, I mean, it's quite actually, how to say, attractive for from the medical application point of view, where you can have more economical implant for many people to access to it. So, what is your plan actually? For example, I mean, I'm very interested in the metal extrusion part. I mean, which part that you are looking to fabricate first for I mean, like for the showcase or for the example that we can use this technology to do that, or what is the property that concern for that?
Yeah, honestly, we still haven't get to that part because we're still on the beginning. So we're still developing the filament and we're still learning the process. Okay,
Sure.
so we still haven't get there which part of the implant we want to do. Yeah, honestly, yeah.
Okay, thank you. I have seen you publish a few paper in this area, so that's why.
Yeah. We're focusing on those things. We published three papers. Yeah.
Sure.
Like the 5-shot pinning part, the increase the fatigue property. Also, we still starting on that one as well. But we got the equipment, so we want to push that forward as well. Yeah.
Sure. Next question is more technical and also is related to the metallurgy that I think we have published paper together on the MIM of the new titanium alloy. I mean, that is clear that the titanium carbide is the big barrier to get the property closer to the SLM. I think, I mean, I just want to have some kind of simulating discussion. I think what we are doing for this project is to try to minimize that. Would that be something you can share or not? What we are working on, something like, I mean, just because if are there any question, please feel free to ask. But if not, we can. Yeah, that is the project we are working on, right?
Yeah, we
make sure that we can successfully MIM the new powder. Metastable beta titanium.
Yeah, because it's beta titanium. If we have to, if titanium carbide is there, then we have to control it to be small and dispersed uniformly. Yeah, if we can, if we use conventional MIM furnace, the other choice is we have to use the MIM furnace that can do fast cooling, relatively fast cooling, so we can avoid the formation of carbide. Just like when we do SLM on the same powder, SLM on the same powder is fast cooling. So we didn't see any carbide on the SLM side. Yeah. So we are working on that, still on process. So that is why we haven't showed the result, because we still struck. Honestly, we try so many things, so we are still trying. Yeah.
Yeah. But I mean, anyone in the floor that have or interested in this, I mean, I'm sure we are welcome for them to collaborate if they have anything in mind or what they can contribute or help us. Sure. I think we have about 5 minutes. I think there is a question now for you, Dr. Anchiri. Thank you very much if I pronounce your name wrongly, please forgive me. Suchiwa. I mean, I would thank you very much for your presentation. I have one question. How about the challenge of 5-shot pinning? What is the challenge to actually basically improve the property? Yeah.
Okay. For 5-shot pinning, I mean, it has been proved that it doesn't have to be 5 for normal shot pinning and 5-shot pinning. on bulk metal or like bone metal of titanium 6-4, it's already been proved that it will improve the fatigue properties. Now, when it moved to SLM or it's moved to MIM, we have some porosity. So we already do the preliminary study, and we found that the 5-shot pinning will reduce will actually eliminate the layer feature that come with the 3D printing. So that should help with the fatigue properties. And the 5-shot pinning increase the compressive stress, residual stress on the piece, on the part. So we should be able to increase the fatigue property as well. So we did some prelim on the MIM, and we found that it's increased significantly, but still on the ongoing process. So we are, hopefully in 1 year we should be able to show more strong, more details result. Yeah.
Thank you very much. There's another question from Kokun Sasiton from MTech. Thank you for the great presentation. I'd like to ask, if we were to promote the metal extrusion AM technology to tri-industry, which sector do you think is the best fit for this? Thank you very much.
Honestly, I think the metal 3D printing, the best sector is for education. That is the best sector for it, because like the people have FDM machine for polymer. If they can have the filament for metal, they can do the printing as well, and they can send the part to MIM company or powder metallurgy company, sinter company, to do the sintering for them, or they can have their own furnace. So I think what most people use the metal extrusion at the moment, because they're still at the early stage, is for material, for education. But all the researchers and the companies that doing metal extrusion, they were trying to push it into real application as well. So still going on. Yeah.
Okay. One of the sector probably medical.
Automotive should be easier than, I don't think that they can survive the aviation application, but automotive might be able to, we can go to that one. Yeah.
Okay.
Yeah.
Sure. I think it's very fit to Thai industry as well, automotive sector. Yeah. I mean, I think we have 2 minutes for a short question. If you have any question, please raise your hand or type it in. I will read it out for Dr. Anjali to answer. Yes. I don't think it's about. If not, we can leave for the. If you have any questions, still you can still type it in, and then we try to answer it if we have time. And then I think it's good. Thank you very much, Dr. Anjali, and thank you very much, MTech, for organizing this first webinar. I would like to move on to the next speaker, if you may. The next speaker is actually Professor Punrat Lawong Watana from Chulalongkorn University. Professor Punrat is a associate professor in metallurgical engineering department at Chulalongkorn University, and also co-founder of Metallurgy company. Today, Professor Punrat will talk about progresses in 3D printing of titanium and other metals for metallurgical and biometallurgical engineering viewpoint. Yeah, the floor is yours, Professor Punrat. Thank you very much. You are muted.
Good. Okay, well, good morning to our UK partners, and good afternoon to everyone else in Thailand. Thanks very much for really informative 2 sessions this morning from Professor Roger Reed and Professor Anjali. From me, I'd like to share slightly more information on how, as a team, we use the 3D printing of titanium to help over 600 patients through additive manufacturing and the creation of patient-specific implants. So first of all, I'd like to mention the Royal Academy of Engineering and the Newton Fund that gave us the first funding actually was the Leadership in Innovation Fellowship back in 2016. And that kind of gave us the courage to start a company called Meticulously in the early of 2017. And since then, we have also received the Newton Fund through the IAPP with Professor Roger Reed and Professor Chinapat. And then just over the COVID time, we got the Live Advanced program, and now with the TSP program. The photos shown here are the ones from the Live Advanced, which was entirely online, but we were able to meet with a lot of people and the mentors through the Set Square people that have been very, very helpful and supportive. And they also allowed us to be able to meet with a lot of surgeons in the UK and meet with a few NHS people as well, just during the past month. So this image was taken with Roger Reed when he was with us during the IAPP program. And at the time, he also helped soft launch a 3D printing technology center at Chulalongkorn University. Right next to Roger Reed is Professor Supot, who's our dean. And Chetha here is CTO of Meticulously and also my colleague. I'd like to point out Chinapat also was back home. And two gentlemen on your left here, they are actually surgeons, orthopedic surgeons working at Lertsin and Bhumibol Hospital. And on the right here, also a surgeon working at Chulalongkorn Hospital. All the three surgeons now are our PhD students studying biomedical engineering. So it's been a fun and really educating experience for us to be doing Meticulously and also take part in the education, teaching now the surgeons to have their PhDs and work hand in hand with engineers to help their patients. Quickly about myself, I am faculty member at Chulalongkorn University. I was the dean in research back in 2015, and I helped establish MedTech Tech Transfer Office. It was called Medical Technology University Technology Center, and also help establish the Center of Biomedical Engineering Research Center at Chula. I resigned from almost all tasks, but now focusing on the co-founding and the CEO of Meticulously until now. My background is actually in metallurgy. I work with rapid solidification and alloy design for the past 25 years or so. And but today I will not be talking about metallurgy, but also something else that we use metallurgy to help patients through biomechanics design and a lot of work done in cadaveric study, animal study, before we could help the patients. I'd like to quickly trace back to 2017, and that was right after my first experience with the LIFT program in London. And we tried to identify the pain point in implant markets, especially in Thailand. As shown on the left here, it's a crate carrying a lot of small, medium, large size implants. They are fixed size implants, and the hospital and/or the distributor has to hold really costly inventory in order to make sure that they have all the parts available for the patient. And as the parts are small, medium, or large, our bones must be cut to fit with the implants. And the tools are shown on the right, a lot of saw and drills and hammers, everything that will try to break our bones so that it matches with the implant. And as a result, the surgeon experiences long surgical theater time, higher rates of infection, prolonged blood loss, and also long recovery time. And as we see this as a problem, and it's inequality in a lot of countries in Asia, in Africa, that if we do not have access to good small, medium, large size implants, what else can we do? And as a result, we back in 2017, we just set up this area for innovation center. So it was used as an incubator area, first in Chulalongkorn University. And the room here it's literally empty. You see my daughter is running around there. And we had to establish the clean room facility to make sure that the technology is making the implants that are clean and safe for the patients. So finally, we got the GMP certification by the Thai FDA, and through a little bit of clinical trials, we were able to save 100 patients back in 2018, just 1 year after the fact. We worked with 22 hospitals at the time, 34 doctors joined hands, and we had 96% satisfaction rate. The number has now increased to about 99, but the way we want to see ourselves is that when we compare the implants that we have created compared to the standard size ones, to the left here, these are the ones that are available at the point of care. And there are, even though standard sizes, there are some customized implants that are readily available, but usually it takes about 20 to 90 days. On top of that, the cost of the customized implants are very expensive. So our strategy is to promote the implants that are affordable, but also of premium quality. So we are offering the implants at maybe about 10 times less expensive than some of these competitors here. And as we learn more about the healthcare in the world, we also learn that only 10% of the world population, especially in the UK, in the US, and Japan, account for 90% of the healthcare spending. So the 90% left of the world population accounts for only 10% of the spending. So I really feel there should be ways that we could use the 3D printing technology to make these implants that are usually better than the small, medium, large, but also make them available to the 90% of the world population. One of the key obstacles that we have accomplished and tackled is regarding the cost of the biomedical engineers that spend time on the design. So we actually introduced the AI to help with the design. We start from the image processing, the design of the implant, and the actual acceptance of the implants by the surgeons. All of these are done automatically online using our cloud platform. And that saves a lot of cost and time as well. And the doctors would be able to receive the implants design in their iPads, iPhones, or tablets. And once they confirm, we start the manufacturing process and deliver the implants to the surgical theater within 7 days. These are some of the intellectual properties that we have developed during the years. Right now, we have over 24 IPs. And a quick summary of our timeline. Back in 2020, we have started the US FDA clearance, and we have actually accomplished the US FDA approval back in 2021 around Christmas time, actually. And especially in Thailand now, we have accomplished, along with Southeast Asian countries, 660 clinical cases. This is our vision. The 3D printing part is just part of the equation. The doctors, the surgeon would upload the CT scan to our cloud server. And from the cloud server, we upload the files to our manufacturing kiosk. And one could essentially be in the UK. And we use this manufacturing facility to deliver the implants to the NHS system or the other healthcare services around the world. So this is our progress so far, and I could not thank the Royal Academy of Engineering enough for their support since day one. And right even until today, they still continue to give us support through the Live Advanced program and also through the friendships that we have created since 2016. I'd like to thank the team for all of these accomplishments that they have supported me and the team and the vision. And the latter half of this presentation is to quickly go over the clinical cases that we have accomplished since day one. As you see here, we have a lot more cranioplasty cases as we progress. And there are also many of the maxillofacial fixation devices that we use along with maxillofacial mesh. So from head to shin, essentially are the top 3 items. And then we still keep on working with orthopedic and also surgical and bone models. And since the leading number of implants are cranial maxillofacial, I like to spend more time and discuss of how we use 3D printing technology to help the patients. So let's start from the head. For the head, as you see the skull here, it's called cranioplasty. Basically, it's a closure of the skull. And typically we call it crani mesh. And if you work the way down, the actual contour of the face could be reconstructed to be exactly the same. And these are mid-face reconstruction that takes the space. In this particular case, it combines the orbital floor that is underneath the orbits of the eye. At this corner is zygoma, and down here is maxilla part of the bone. So we could actually make all three parts interconnected, just like the original bone like before. The actual part of the eye, it's called orbital reconstruction. We also make that. And down here, mandible plate, we use this to do the manual reconstruction, and sometimes with prefab. I'll go over that example in a minute. For the crani mesh, some of the design could be as large as the whole forehead. We have done one case of the whole skull actually, and the design could be personalized. The clip here could be designed wherever the surgeons want. Sometimes they want to hide it under the eyebrows, or where the skin is thicker or the skull is thicker. Show some of the pictures, and this is the whole forehead for some of the patients. Apologize, there are some bloody photos, but as you see here, the whole forehead is missing. So we have to pull back the skin and install that, and then pull the skin back. As you see, it restores the original curvature just like before. Then this is the design that we discussed with the surgeon in order to work on the tumor. We could provide them with the surgical guides with the exact same holes that we would install the implants on later on. So the surgical guides are patient specific, and the doctor could do that craniectomy. That is the act of removing the cranial. That's called craniectomy, and he could do that with precision. And this is one of the cases that we had to remove the tumor, and we close back the skull using the titanium crani mesh. And the pre-op and post-op results, as you see, we could restore the exact same curvature just like before. Also for MRI and CT scan imaging, because the implants are designed to be so thin, we could allow the doctors to see the pathology of the brain just like before, and no distortions through the CT or MRI. Move on to the face, and this is called the fasci mesh. We create the mesh for the patient just like the skull, and this one includes both frontal and zygoma reconstruction. And we also have the the cutting guides for tumor resection. And once we remove, we install the titanium. As you see here, the step is remove. Once we remove, we reinstall the mesh. This is another case for mid-face reconstruction. As you see here, the brown area is the tumor, and we work with the doctors to find where the incision would take place, and then we create the surgical guides. And once the doctor cut it along the surgical guides, he would be able to install the mid-face reconstruction mesh. And this is the patient, and now she's really happy and working just like before, even though she had this tumor removed. This is another case. This is a patient with mid-face reconstruction. As you see here, we also remove the tumor resection and recreate the patient-specific implant. I'm going to skip some of the images because they're quite graphics. Our team is too used to this because we see this every day, and I apologize for that. This is for the orbital floor, and a lot of times the patients would have double visions. They could not work, they could not read properly because the eyes are at different positions. So we would be able to reposition the eyeballs and allow them to be able to see just like normal again. So these are some of the cases. As we move down to the shin, and we have a lot of these cases in Thailand, in Taiwan, and in China. And basically, we have to remove, as you see here, there's some sort of tumor that took place where the blue and the yellow bones are located. So we have to completely remove it. And we have to restore the curvature just like before. And the blue and the yellow pieces are actually grafted from fibula. Fibula is a bone that is located on your leg. So as you see here, the red area has to be dissected. The blue is to indicate the direction of the dental implants. We could plan that ahead of time. And as you see here, the mandible goes around, and the blue and the yellow bones here are from the fibula. And we have to design so that the dental implant is directly in the middle, and the two screws that coming from the bone plate here would miss them. You would be on both sides of this dental implant. It's the same for this one here. So everything has to be planned ahead of time, and 3D planning is really helpful in this particular aspect. And we do biomechanic design to make sure that the implants are strong enough to withstand the loads. And we do about safety factor of more than 200%. So as you see here, that is the fibula bone, and we have to graft two pieces to install them like here. We also provide the surgeons with the surgical guides. The white area is plastic, 3D printed, and the slits here are titanium. So the drills could go inside here, and it could be pre-drilled for final shape correction. And as you see here, the knife goes both sides. And down here, there's also the knife guide for cutting into two pieces of really unique shapes. And then the holes are pre-drilled. So all these holes here, 1, 2, 3, 4, and then 3 on each side, are actually aligning with the final bone, the final holes here. Okay, so we were able to plan ahead of the time. So in this particular case, there are 4 fibula pieces. All of them have really unique shapes. We cut them in fibula and reconstruct them like this. And as you see here, the bone plate goes around and lock the fibula into positions. And these drill holes are prepared ahead of the time so that the dental implants could be installed afterwards. I'm going to skip a few pages as we are running out of time. And some of the cases, the doctor opts for a basket like this and bone graft inside. And that's also another possibility. So we basically serve as the platform, the technology platform relying on 3D printing of titanium and AI design of the implants to work with many, many surgeons in Thailand and in Asia now. And I'd like to really thank to all of our surgeons who have worked to help their patients and allowed us to be part of it. Thank you very much for your time today. And I'll pause here in case you have any questions. Thank you.
Thank you very much, Dr. Bunrat. This is very inspiring presentation. I can see how the impact of the research that you are working on actually impact to the patient around the world now. And very many congratulations to your success. Are there any questions for Professor Bunrat? Please type it in or raise your hand. We allow you to speak. Yes, please. I mean, you are welcome as well in the panel if you have any question for Professor Bunrat. Yes.
I can start with that. Yeah.
Sure.
As I understand, Professor Bunrat implant is titanium 6.4, right?
Yes.
Yeah. You have any plan of doing like the beta titanium as well?
Yes, that is one of the main goal is to adopt the new alloy. Like Roger mentioned before, in order to use the new titanium alloy, it requires a lot of work. Even the design of the implants themselves, we have to do a lot of cadaveric study, animal studies before we could use them. Even that with titanium 6.4. So yes, I do have a plan, but I'm waiting for alloy to finalize the alloy and the capability to use them in implants. And I think we should open this for future collaboration as well, Roger.
Yes, this is the plan for the TSP project actually. As you may recall from the application, we are designing now a kind of biomedical test kit. I mean, collaborate with Oxford as well. One aspect. Another aspect, as you said, the fabrication of the I mean, kind of test implant that we are looking at the moment. Yeah, so that's what we are doing, Dr. Anjali. Thank you very much. Roger, do you have any question for Professor Bunrat or not?
No, I just want to make a comment that actually I think the progress which is being made is really amazing, and congratulations to him and his team, because it's very impressive.
Indeed, yeah.
Oh, thank you, Roger. We could not have done this without you. Thank you so much for all your support in the past years. Thank you.
Yes, are there any question for Professor Bunrat? Please type it in, or you can, I mean, you can ask in Thai if you want as well. Yeah, please raise your hand, or we will give you permission to speak. Yeah.
Could I just ask one question of Bunrat? I think you said that you had already made implants in different parts of the world. Is that correct?
Yes, Roger. We are now in commercial state in 7 countries, and we're hoping to reach about 15 by the end of this year.
Okay.
But mostly in Asia.
In Asia, yeah.
Yes, but we also would like to expand this into the UK. We received the support from the Department of International Trade from the UK government to, let's say, find business opportunity if we could use UK as the manufacturing base for Europe and also to Africa. So we are still deciding on that. Yes.
Thank you.
Oh. This is very exciting, I would say. I mean, in the meantime, if not yet having question, I would like to, I mean, on behalf of all UK partner, Roger from University of Oxford, and also Alloy Company, and myself, at the moment at Queen Mary University of London, I'm very thanks for, I mean, collaboration with MTech and Chulalongkorn Medically very much in the past year. So I think we've been discussing this since 2017. Both of you, or probably Professor Bunrat even earlier than that. And this could not happen without your hard effort. And also thanks very much Royal Academy of Engineering for the support throughout the years, I mean, and up until now. And I hope many more collaboration to come in the next following years. Then I think yeah, just give everyone a background. This is just a joint seminar between 2 projects that have shared the same UK partner. Actually, we very fortunate and lucky enough to have these 2 projects in this I mean themes of research on a novel titanium alloy for biomedical application, and that's why you see a lot of a logo that combining 2 projects together. And just Professor Dr. Anjali may give a bit update on the following how to say event that we're going to have. I mean, first is online, another webinar, and in person, which will be quite big because we have jointly organized, hopefully early next year in Thailand. Yes, please, Dr. Anjali.
Yeah, so this is a series of seminars. So this is the first one, and then we have the second one, the webinar, probably in August. Okay, so and at the beginning of next year, hopefully the UK team can visit us in Thailand, and we will organize an on-site event. So everyone is invited. Yep. Thank you.
Sure. So, I mean, around summer this year, we'll have a second webinar before the first, I mean, in-person meeting. Actually, is going to be big in the central of Thailand, I mean, Bangkok, for sure. So we will, I mean, I take this opportunity to invite everyone here. I mean, we will meet a medical doctor, academics, industrial people, I mean, all that. So please, I mean, keep an eye on our announcement, and then we will welcome you to the event in the very near future. And so I think if not, we can thanks everyone here, and then we will see you again in the very near future, and then we'll keep you updated on the next event for these TSP projects. Thank you very much.
So, thank you, everyone. Yep.
Thank you.
Thanks to the
Bye.
MTech team as well for hosting this webinar. Thank you.
Yeah, thank you. So next time
Thank you.
is Chulalongkorn University.
Chula.
Okay.
We
Yeah.
will try. We will try
Okay.
our best.
Thank you, Roger.
Yes,
Thank
sure.
you,
Thank
the
you very
audience
much,
as well.
Roger.
Thank
Yeah.
you.
It's
Thanks,
lovely.
everyone.
Yeah. lovely
Thank
to see
you.
Thank you.
Nice to
Thank
meet
you.
you all.
Okay,
Thank
bye-bye.
you.
Bye bye.
Bye.
Good day,
Bye.